Hey, I'm Roger. I'm from Nous Research. We train open source LLMs. So today we're going to be talking about a little bit about reinforcement learning, specifically multi-agent. We're going to start with an overview of what are we exactly getting from reinforcement learning versus supervised learning. Then we're going to talk about the path towards self-improvement, and then we're going to end by talking about an open source multi-agent RL SDK that we've been working on. So let's start with supervised learning. You guys have all probably seen this before, but you have a model, a loss, and some data set. And your goal is to train the model by incrementally making small improving changes to the parameters to decrease the loss on this data set. So supervised learning kind of looks like this. If you take one weight out of your model and hold it, and allow it to vary, but hold all other weights fixed, and you plot the loss on your data set on the y-axis, then and you have enough like bells and whistles on your gradient descent, like momentum, then gradient descent kind of behaves like a ball rolling down this like hill, which is the loss landscape. So one step of training is like you hit play on this, and then you let the ball roll a little bit, and then you hit pause, and then that's where the ball like ends up. And this only kind of works because this loss landscape is kind of like smooth and nice. Does this work for all loss functions? Like, so let's consider something else. What about accuracy? So this is kind of like the grade on an exam. If there are n questions, then accuracy takes on these n+1 possible discrete values, 0 over n through n over n. So what would it look like if we made the same plot for accuracy instead? It would look kind of like this. So accuracy is going to be a piecewise constant function of that weight instead. And the ball doesn't roll anymore. So what does this actually like mean? It's like kind of like whenever you have this piecewise constant node in your compute graph, so whenever you have this like picking operation, then sort of supervised learning is kind of stuck. It can't backpropagate through that compute node. It zeroes out the gradients. So this shows up in language modeling. If you're doing greedy sampling, let's say, and you're picking like the most probable token at each step, you can't backpropagate past that choice of token. And then there's this other like mixture of experts thing, like the chosen expert's also a piecewise constant function of the router weights. So you have to gate the output of the expert by the router by a function of the router weights for that expert to be for the router to be trained. So here are some limitations of supervised learning. It only works with losses that satisfy certain nice properties, so like differentiable almost everywhere, convex, smooth. And supervised learning doesn't play well with objectives over these multi-step trajectories that don't decompose well into single-step objectives. So the main medium with which the modeler communicates intent to the model, like how they want the model to behave, is data. In particular, they need expert examples of what is good, and it's kind of there's no way to demonstrate what is bad to the model, so what behaviors to avoid. And another property of supervised learning is just that if the like the level of the experts is sort of the ceiling that you would expect for the performance of the model. If the model outperformed these expert labelers, it would be kind of surprising. So now we move to the RL. So we have this like agent. It's in a state, and it can observe the state and take an action, and then the state updates and also receives a reward. And our goal is to learn a policy that controls the agent to maximize the sum of future discounted rewards over time. So language modeling actually maps onto this setup very nicely. The states are simply the text prefixes. So the initial state S0 is like the prompt. The actions are the next tokens. So the action space is the vocab. And then a policy in this environment is simply like exactly what a language model is. It's a map from the text prefix to a probability distribution over the actions, the next tokens. So all you have to do is specify your favorite reward function, say like how funny your model's generation is, and you can optimize your model against it with reinforcement learning. So we can take a look at like the RL objective. So let's say you've like decided your favorite reward function. The RL objective is simply to maximize the expected cumulative discounted reward over time. And the special thing about this is the expectation part. This is the expectation taken over the policy. And so in this sense, the rewards are actually only just an abstraction. The rewards can be anything. They can be discrete. They can be like the accuracy, the points on an exam or something. But the key trick here is that you're going to smooth this out eventually into this differentiable function by taking this expectation over the policy parameters. But still, like this abstraction is quite nice to have because humans kind of communicate, can communicate kind of rewards very easily, whereas like designing losses is kind of hard. So for example, teachers will give like grades to their students. They'll give like grades on exams to their students. These are like discrete quantities. And that's an easy way for teachers to communicate like how well a student is doing. So in that sense, like this reward abstraction is a very human thing to consider. So our goal is to like find the argmax of this with respect to the policy parameters. And of course, the only optimization tool we have is gradient descent, so we can take a derivative of this. What happens when we like differentiate this is that like there's a trick here. Under certain like regularity conditions, you can like move this gradient into the expectation, and you get the expectation of gradient of something. Now, like when you have the expectation of like something, you can approximate it by just taking like samples of the thing on the inside and then averaging them by the law of large numbers. And that's exactly like the thing that we do. So this implies like one of the most natural and simplest reinforcement learning algorithms, that we sample a rollout, a sample of the thing on the inside of the expectation, and then we calculate the thing on the inside, and then we update the parameters by this. The algorithm used by DeepSeek to train R1 GRPO is very similar to reinforce. It only adds on this reward normalization based on groups, and this PPO style clipping if you want to sample a large batch of these rollouts, and then take like mini optimizer steps. And each time you take a step, you kind of go slightly off policy, so to be careful about that and clip the objectives, or clip the amount you're stepping. So how does RL address the limitations of supervised learning? So it works with nearly arbitrary rewards, right? You can have whatever rewards you want, discrete, non-differentiable, like whatever. It works well with objectives over these multi-step trajectories. And the design of a reward gives this additional medium for modelers to communicate intent to the model. So you can kind of like come up with your favorite reward function as like, and I guess like in a very human way, and just like tell the model like what you want. You can demonstrate what's good in addition to what's bad. The model outperforming the actual like humans is very possible and has been done. And the model learning self-correction is like totally unsurprising, right? So you might have seen examples of like your RL on like a car environment. It goes onto the grass and self-corrects and goes back on the track because it continues to receive a reward. So it's like O1 R1 style self-correction in the LLM space is probably kind of expected. But what about self-improvement, right? So we've seen cases in RL of self-improvement. So like AlphaGo, AlphaZero. How about with language models? So what would a self-improving agent on, say, math look like? So for example, we might need a math problem generator, a math problem solver, and then also a math solution verifier. And in order to not bottleneck the progress on the other two, all three of these have to improve, right? So if your verifier like lags behind the others, right, then it like might be noisy and give a noisy signal. Or if your generator lags behind the others, it's not generating hard enough problems to keep improving the other two. So this is a multi-agent setup, and it's a kind of hard multi-agent setup because it's like the generator and solver are kind of fighting against each other, and it's like a mini-max optimization problem, and this is kind of unstable, like GANs, right? So we also need kind of easier multi-agent environments for LLMs to build up incrementally to be able to like deal with these harder multi-agent problems, and like to test if even like the training is working and stuff. And so that's the motivation for like producing one of these multi-agent environment SDKs. So it's easier for everybody in open source to develop these multi-agent environments. So everyone has a slightly different way of doing multi-agent, right? So like you might call your player ID like self.player ID, or somebody else might call it like self.agent ID. And you might only like return like the step function, the step method might only return like part of the 5 tuple from Gymnasium. And we think that's totally fine. Everybody can have their own like way of doing multi-agent environments. At the environment level, we don't care. But instead, where we do care, where we do want standardization, is we're at the rollout level. So we believe that like one way to standardize is to have some method like .autoplay or something in these environments to output a standard trajectory history that's ergonomic to a trainer. So we provide a wrapper to do this, but we would be perfectly happy if everyone just like adopted m.autoplay. And a wrapper simply looks like this. You define your multi-agent environment, and then you can wrap it in autoplay, and then you can call .autoplay. This is an async version of it where it starts a server simultaneously. So it starts a server, it shows some output from the game, and that's your rollout. And then you can actually save the history. This is the server. It logs the history, and if you're like a serious front-end developer, you can make a nice front-end for this. Some other sharp edges we handle. So sometimes like you're making assists, like you pass to your friend and they make the goal, and then at that point, both of you should get the reward. You should get the reward for the assist, and they should get the reward for the goal. So we handle that. You can decouple outcome and process rewards. So if you score a buzzer beater, that player will get the reward for the basket, and then and then the whole team that won will get the reward for winning. This is the end of the talk. So just to talk about some other stuff we're working on, we have this modular and hackable async multi-node RL trainer built on Torch Titan and SGLang. We're working on computer use with backtracking, and then this is not a new sponsored project, but one of our student researchers is also working on R1 style reasoning model with discrete diffusion language models. Thank you very much.